welcome to our Quantum Bits, Bytes and Insights event. This is a lunch and learn session where we invite you to join a tour of our labs. And it's really fantastic to see such a great turnout, people with healthy interest. I should inform you that this event is recorded, which means that you have the possibility of watching it again and again, if you please. First, I'll introduce myself. My name is Sofie Lindskov Hansen, and I'm a quantum business developer here at Sparrow Quantum. And although my roots are actually in experimental quantum photonics, it has been quite a while since I worked in the lab. And that's why I've invited my colleague Max to take you on a tour of our optics labs and give you an inside look at the work that we're doing here at Sparrow. And Sparrow is a spin-out from the Niels Bohr Institute at the University of Copenhagen, and we are really proud to sort of build upon the cutting-edge research from the university to deliver a world-leading deterministic single-photon source. And this is a technology that's expected to become like a building block of the future quantum technologies spanning from quantum communication, computation, simulation over sensing and metrology. And our team is rapidly expanding. We have 25 full-time employees now, and most of them are working really hard in the labs every day. And today you're fortunate enough that Max will give you a lab tour and a glimpse into the characterization lab, where we make sure that our single photon sources live up to the highest of standards in terms of indistinguishability, purity, and efficiency. And after the lab tour, Max and I are very happy to answer any questions that you may have. So please just post them in the comments and then we'll take a look at them. So without further ado, I'll hand it over to Max. Enjoy the tour, and I'll see you again in a few minutes.
Hi, I'm Max, a photonics engineer here at Sparrow Quantum, and today I will show you a bit of our characterization lab. Please follow me.
As Max heads to our lab, let's uncover what he's characterizing. Before our deterministic single-photon source chip is delivered to customers, we rigorously test its performance to ensure it meets our end users' predefined specs. We can deliver over 95% photon indistinguishability and a near-unity purity with a G20 under 1%, all demonstrated in our lab before shipping. Now that Max has arrived, let's learn how to test the on-chip single-photon source.
So to excite our quantum dot, we have an outcoupler here that will prepare the beam diameter. That beam is being directed here, where we have some power control and some imaging system, but mainly we have a quad wave plate and half wave plate here to prepare the polarization in the state that we want to excite the most efficient way the dipole of our quantum dot. Then here we have a beam splitter plate that is directing light directly onto our objective and our quantum dot, which is inside the cryostat. And then all the single photons will be emitted upwards through the same objective, going through the beam splitter here. And then some polarization optic will allow us to filter most of the scattered light coming from the laser. And finally being coupled into that fiber here. Now here I just inserted a white light source that will send some light to our objective to shine the whole space of our objective. And all the light is being imaged here. So on the screen here we can see that when I turn on the white light, the structure is appearing. With a photonic crystal here, a waveguide, and a diffraction grading outcoupler. So we excite the quantum dot here, and the single photons will be emitted out from the diffraction grading. Here we have our Hong-Hu-Mandel interferometer, where our single photons are coming from that single mode fiber. They're being split here by that polarizing beam splitter, and then we have two paths. The first one is going here into that fiber, and the other one is going through that quad wave plate and then into that single mode fiber, and then we have a delay line here that is matching the distance between two pulses of our excitation laser. And then the two beams are being recombined here on that fiber beam splitter, and then the signal is then being split into the two single mode fibers that are going to our single photon detectors. One of the key elements to get the most of the signal source is to filter out the light from the phonon sidebands. And to do it, we use an Etalon filter that has the bandwidth which is matching the one of the quantum dot. So here we can see that the signal is being filtered, and it's quite neat around the zero phonon line of the quantum dot. And when I remove the echelon, what we will see is that the phonon psi bands will appear on the signal of the spectrometer. Here we can see that at the bottom of the zero phonon line we have a broadening of the spectrum, which is coming from the phonon psi bands that previously we could filter out. Now we have a look at our voltage source, and that voltage source applies a bias on the diode junction of a quantum dot, and that bias will basically set which wavelengths will be resonant on our quantum dot, and how to excite it, and also how to make it more stable for the noise level that is around it.
Here we end the quick introduction to our characterization lab. Now back to the live studio, where Max is ready to continue the conversation and answer your questions.
All right, welcome back from the lab, Max.
Thank you.
And thank you for that, the tour.
My pleasure.
So we have received some questions in our comments, and I think we should just dive right into it. The first question that we received is, why do we need a voltage source?
Yeah, so as you might have seen, the quantum dots are embedded in the diode structure, and this structure it enables to control the charge state of the quantum dot. So in our case, we want to look at the neutral exciton, and that allows us to really have a good control of the charge environment, and really to decrease the charge noise, and to increase the indistinguishability of the quantum dots signal that we get.
Yeah, thank you very much. And along those same lines, we have a question asking, which voltage stability do we need?
Sure. So something that we have tested is different voltage sources with different voltage stabilities, going from hundreds of microvolt RMS to up to a few millivolts. And we've seen that up to 5 millivolt RMS, we still have a good signal with the 95 indistinguishability that we promise. So up to that is fine. If the user would need to have a high indistinguishability between successive photons in a microsecond timescales, we might need to rediscuss. But for one-to-one photon, 5 millivolt RMS is okay.
Okay, thank you very much. And another question we received is, what kind of optical filters do we use?
What we use right now, it's Fabry-Perot cavity echelon filters, which have a bandwidth between 3 to 10 gigahertz. And the FSR of these filters is usually between 100 and 200 gigahertz, and that works fine for us.
Mm-hmm. And the reason that we need a filter is because?
It's because we need to filter out the phonon psi band signal coming from the quantum dot. So as you have seen previously in the lab, when we remove the filter, the signal is a bit broadened out on the red side. And if we don't have that, that will decrease the indistinguishability property of the single photons.
Yeah, thank you very much, Max. Another question, what are the collection losses of the setup?
So in our case, the setup is not optimized to get as many photons as we could, because we need to do a lot of changes between the different parts of the characterization of the single photons. So in our case, the efficiency is maybe about 20%, but we've seen that if you want to really go for the highest specs, the highest count rate out of the single photon source, selecting really the best optical components, you can achieve more than 80% efficiency, really just optical setup.
Mm-hmm. And how much is actually lost at the outcoupling grading? What's the efficiency of that?
So one number that we give to define what we call the fiber brightness of the quantum dot, of the chip itself. It's what's the probability of having one pulse of a pulse laser that will transpose into a single photon emitted out of the chip, and that we can couple into a single mode fiber, because that's what the user wants at the end. And that number is completely independent from all of the losses coming from the setup, because as I said, that can vary from one user to another. And in our case, we typically provide sources that have above 20% chip efficiency, so that can be coupled into a single mode fiber. But we know that we've measured in the lab efficiencies up to 50%, and we really think that with the technology we have, that in the future that number will be increased even.
Okay. Nice. And what is the lifetime of the quantum dots?
So the natural lifetime of quantum dots, it's a few nanoseconds. But our chip is made out of a photonic crystal in which the light-matter interaction is enhanced, and that's increasing the spontaneous emission rate of the quantum dot with an effect that is the Purcell effect. So we have a Purcell factor that will decrease the lifetime of the quantum dot, going down to 200 to 300 picoseconds. That's what we aim.
Okay, yeah. And which laser do you use to excite the quantum dots?
For the applications that we have, we typically use a pulse laser, so that we have one pulse that will generate a single photons. And in our case, we use the PQQ laser from Refine Lasers. That works fine for application, but that can vary from one user to another, depending on what you might have in the lab and what you need also in terms of rep rate. But what's important is that the laser has a spectral overlap on our quantum dots emission wavelengths, and then that the rep rate is according to the needs of the user.
Okay, thank you very much. Then we have another important question here. Do you provide the free space setup to operate the single photon source?
So we do not provide the whole setup around the free space chip that we sell right now, because that would be maybe too much. But we accompany the customer in such a way that when we will deliver the chip, we make sure that the setup is more or less ready to be able to have single photons out after 2 days, 3 days of installation. So we do not sell the setup, but we really provide the guidelines that we have also to increase the efficiency, the collection efficiency, the filtering efficiency, and all of that. But I must also say that right now we're also working on a fiber chip. We have the first prototypes running in the lab that works pretty well, and that will really emancipate the user from all of that free space optics that you've seen in the lab, such as that you just have one fiber in, one fiber out. You will still need to have the filtering that I showed, but that will really increase the ease of use of the chip.
And we're actually also working on a full plug-and-play system that sort of contains everything.
So that's also something that we're working on, indeed. So what we want is that for a user, we could just provide a big rack device composed of a cryostat, a laser, the electronics to control it, and then we just press a button and you have a single photon out. So that's what we're also working at, indeed.
Pretty cool. And then the last question for now is, which wavelength are your single photons emitted at?
Sure. So for historical reasons, the quantum dots that we have, they emit in the 910 to 970 nanometer. Typically, customers are interested in about 930 to 950 nanometer. But we are also working towards extending that range up to the telecom wavelengths, up to 13 and 10 nanometer, because that will allow to open up really the field of quantum communication, where such wavelengths are required to decrease the losses in fibers for longer distances.
Yeah, cool. Then we have another few questions ticking in now. We have one question here. How do you change the path length difference of the home setup?
Yeah, so right now on the home setup, we just measure typically we measure the interference between two successive photons. So we have two branches, and one of the branches has a delay line, which is an optical fiber, which is more or less matched at the rep rate of the laser. And on top of that, we have a small delay line that we can tune to really match the perfect delay between two successive pulses. And we are also working to expand that measurement to not 2 successive photons, but 100 successive photons. And for that, we have longer fiber delays that we are integrating in our protocol.
Mm-hmm. Yeah, thank you very much. And then we have a question here. What is the efficiency of the source with the echelon filter?
So if the efficiency is what I described before, the fiber brightness, really what's the probability of having a single photon emitted from a pulse coming from the laser coupled into a single mode fiber, that efficiency can vary between 20 to 50% according to how much effort we spend investigating for the right quantum dot. And then the echelon filter, it depends on the transmission it has, but typically it's about 90%. So you remove 10% of the number I said, and that's the number you can get.
Cool. And does it change with each measurement?
No. The source is super stable over time. We've seen that over months of usage, even almost close to a year, the source is super stable.
Yeah, it's pretty good. And then the last question here is a really good question. How do you place the quantum dot in the photonic crystal?
So that's the way we have done historically in Sparrow. We have a wafer material with a lot of quantum dots that are grown at different positions. And we build the structures around them. But we don't align the photonic crystal on a specific quantum dot. We just build the structures. And then according to the need of the customer, we will look for dots that have the properties that the customer wants. So high indistinguishability, high purity, and high fiber brightness. And in a chip, we characterize one quantum dot for the customer, but typically we have almost 100 structures in which quantum dots are present. And each of these structures have, again, tens, hundreds of quantum dots. So we just select the ones that are better for the customer, but we don't place the quantum dots specifically at the point on the chip.
So the quantum dots are formed in like random positions, and then fabricating the photonic crystals on top, and then we find the ones where there's a good overlap.
Precisely.
Yeah, perfect. Yes, I think that was the last question for today. Thank you very much for joining us during your lunch break. And this is a recurring event, so keep your eyes out for a repetition of this event. And thank you very much, and have a lovely day.
Thank you. Bye-bye.
Thank you.